Okay, this is the midterm review for Chem 7L for spring 2020. Okay, let's just jump on into it. Report the following arithmetic result with the correct number of sig figs. Select one. Okay, so let's take a look at what we have. We have some brackets out here, some internal brackets. And basically, if we see this, we have two things being multiplied in the bracket and then multiplied by this. So basically, what we need to do is know how many sig figs is each one of these parts, and then forecast that to the answer. So let's look here. I have 4 sig figs on top. I have 4 sig figs on the bottom, which means this is going to have 4 significant figures. So let's look up top here. What are we going to have up top? We're going to have 9.253 minus 8.376. That's given here. It's 0.877. So this up top is 3 sig figs. Down the bottom is 4, which means this whole division is ruled by the smaller number. So this has 3 sig figs. When we multiply these two together, once again, 3 sig figs wins. And then we'll multiply it by the log of 34.44. There are 4 sig figs here, but that actually drives it here to, because the one in front, it'll be 5 numbers, but 4 sig figs. But once again, 3 is still smaller, so we can only keep 3 sig figs in the answer. So the answer is A. Report the following arithmetic results with the correct number of sig figs. Okay, so basically, once again, we have the same parenthesis structure. We have some number added to some other number, right? And then those together are going to be added to this, right? So it really doesn't matter if these outer parts are in parentheses or not. I just want to make sure I give you the math. So let's see what we got here. We have simple division. So we have 6 being divided by 5. So this means that whatever this is can only have 5 sig figs. So let's look at that. That's here. We can only have 5 sig figs. So it's 3.5935, right? So that's my 5th sig fig from this, right? My 5th sig fig. But remember, we don't throw anything away to the end. Okay, and that's going to be added to, what do we have up top? Well, we have some subtraction. So let's do that subtraction. It's right here. But let's line it up. 7.98332 minus 7.98176. And that's going to give us a 0.00156. So there's only 3 sig figs up on top. So there's 3 sig figs here. Being divided by 5 sig figs means whatever this is can only have the 3 sig figs. So this can only have 3 sig figs, and here is that math right there. So this can only have 3 sig figs, so 0.268, there's my last sig fig for that, 28555. Okay, I have the logarithm, and this logarithm is going to have 6 sig figs and 7 numbers when we put one out in front. So we have 6 sig figs plus the decimal place, so 3.827720. Right, that's my significant figure, 703. So when we add these together, we get 7.6895938, yada, yada, yada. Remember, where is our largest error? It is in this 3rd decimal place, so we can't do better than this. So our 3rd decimal place will be this, because of course this 5 will cause that 9 to round. Number 3, report the following arithmetic result with the correct sig fig. So we have a logarithm of some number times some number. Okay, so let's see what we have here. 5 sig figs, 4 sig figs, 1, 2, 3, 4, 5, 6 sig figs. So whatever this is in here, we'll have 4 sig figs. Okay, so let's do that logarithm of this right here. It's going to have 4 sig figs, so 2.7115, right? 41452. And remember, it's at the 4th decimal place, so 4 sig figs, 5 numbers altogether. And that's going to be multiplied by this difference, right? So let's do that difference. 9497.32. We're going to minus 87.65345 from it. It's quite obvious to see we can't have more than the second decimal place. That math is performed right here down the bottom. So we got 9409 decimal 6665. So that'll round up. So we're multiplying 1, 2, 3, 4, 5, 6 digits times 1, 2, 3, 4, 5 digits. Okay. So remember, once you have a logarithm, you still have 5 numbers there. So that's going to dictate how many numbers we can have in the answer. So it's 5. So it's D. This is a challenging one. You have to go back and look at those log rules. Right? Once you do math with a logarithm, it loses its exempt status from being a logarithm. Okay. So for the ruler below, how many significant figures should be reported for the measurement of the bar below it? Okay, well, let's do the math. What is this edge? It's going to be 11.230. We'll call that a 5 and then maybe a 7. And we'll minus 11.2271 over 2, which means 5. That's a 4. 3 goes to a 2, 3, 0, 0. So this will have 3 significant figures. Okay, moving on. Select the definition of significant figure. Select 1. All the certain digits that follow the decimal point. That is not correct, right? That's not the definition of significant figure. All the certain digits that precede the decimal point. No, we can have significant figures that are right at a decimal point, right? All the certain digits plus the first uncertain digit, right? This is what we talked about in class. This is exactly what the definition of a significant figure is. All the certain digits plus 2 uncertain digits. Why add more uncertainty when we only need 1, right? All the certain digits and no uncertain digits. Absolutely false. So the answer is C. Report the following arithmetic result with the correct number of sig figs. Select 1. Okay, so remember how we solve these? We set everything to the power of the answer. So let's start on the left. We have 4.83601 times 10 to the minus 11. Here we have to the minus 15. So to the minus 14 would be moving the decimal place there. 14, 13, 12, 11. So 0.007600159 times 10 to the minus 11. This is to the minus 14, 13, 12, 11. So 0.009142 times 10 to the minus 11. And 13, that would be 12 and then 11. So 0.032021. Add them together. So what do we have here, right? We have, what's our smallest? We have 5 decimal places. Here we go out to 1, 2, 3, 4, 5, 6, 7, 8, 9 decimal places. Here we go 1, 2, 3, 4, 5, 6 decimal places, and here we go 1, 2, 3, 4, 5, 6 decimal places. So 5 is the limit. We can't have more than 5 decimal places. So 4.877993 times 10 to the minus 11. D is our answer. Okay. Moving on up. A student calculates the average and standard deviation for the pressure of unknown gas as 73.278623 plus or minus 0.029784. The dial for the gas meter is shown to the right. How should the result be presented? Rule 1. Does this begin with a 1 or a... your error can only have one significant figure unless it begins with a 1 or 2, so keep 2. Okay, this begins with a 1 or a 2. So let's write it. 0.029. That 7 will cause it to round up. Okay, so it'll round up to 30. But now we no longer begin with a 1 or 2, so we have to get rid of that 0. Rule number 2. Are we doing better? No, I'm sorry. Our reported answer can't be any more precise than the reported error, right? Our average can't be reported. So it has to be to the second decimal place. So it'd be there, and that'll round it up. 73.28. Rule 3. Are we doing better than our instrument? Well, let's see what the resolution of our instrument is. Let's just pick a point. Boop. Okay. What is that reading? Well, it's 73. There's a decimal place. So that'd be 0.12. I'll call that 0.3, and then maybe 7. Which means if that isn't reading, we can get off this, right? Our error is to the second decimal place. So cool. The other thing is, remember, if we have 0.1, 0.2, 0.3 digrations, but we don't have point digrations for the 0.01. So that's also another way for you to figure out what that is. So now we have to compete it. Which one is bigger, right? The 0.03 is bigger than 0.01, so we keep that. The answer is Bravo, B. A student calculates the average. The standard deviation for the pH of an unknown acid is 7.823654 plus or minus 1.37455. The pH meter shows 2 decimal places. How should the result be presented? Your error should be reported with, rule 1, your error should be reported with one significant figure unless it begins with a 1 or 2. Does it begin with a 1 or 2? Yes, it does. So it should be 1.4, because that 7 will cause that 3 to round up. And then we must match it with our error here, so 7.8. Okay, rule 3. What about comparing it to our machine? Well, our machine says it's plus or minus 0.01. So what's bigger, 1 or 0.01, right? It's really the 1, so there's our answer. A student calculates the average and standard deviation for pH of an unknown base is 7.65935563 plus or minus 0.0297426. The pH meter shows 3 decimal places. How should the result be presented? Your error should be reported with one significant figure unless it begins with a 1 or 2. Okay, this begins with a 1 or 2, so we're going to report 2.029. Oh, that 7 is going to have it round up. Oh, we no longer begin with a 1 or 2. Okay, rule 2, we now must match our answer to that, so not a problem, 7.66, because that 9 will cause that 6 to round up. Now we have to compare it to the meter. Our meter's in our third decimal place. What is bigger, 0.03 or 0.001? Of course, it's the 0.0376, so A is our answer. A student measures the pH of an unknown solution 3 times and obtains an average of 9.72465 and a standard deviation of 0.00345333. The pH meter is shown below. How should you report the result? Our result should be reported with one sig fig unless it begins with a 1 or 2, so 0.003. 4 does not have it round up. Our answer cannot be more precise than our error, so third decimal place, 9.7. 2, and that 6 will have it round up to a 5. And then are we doing better than the instrument? Our instrument error is to the first decimal place. So yes, we're doing better than our instrument, so we can't use this. We have to use the instrument error. So our answer will be 9.7 plus or minus 0.1. An acid has a Ka value of 4.6493 times 10 to the minus 8. The corresponding value for pKa is shown on your calculator, 7.3326066638. Report this pKa with the correct number of sig figs. Select 1. Okay, so this is the Ka value, right? This is the equilibrium constant. And we're taking a pKa, right? Remember, a pKa is the negative log of the Ka. So we're going to take a logarithm of this number. So how many sig figs do we have here? 1, 2, 3, 4, 5 sig figs, right? So we have 5 sig figs, and we have to maintain those sig figs to the right of the decimal place. So which one of these has 5 to the right of the decimal place? Let's see. 1, 2, 3, 4, 5. Boom. Gotcha, right? 1, 2, 3, 4, 5, and that 6 has it rounds up. Yay. Okay, the pKa of an acid is reported as 6.43. The corresponding value for Ka is shown in your calculator is 3.71535 yada yada times 10 to the minus 7. Report the concentration with the correct number of sig figs. Remember, a pKa, this is a logarithm, so the sig figs are all to the right of the decimal place. In this case, 2 sig figs, which means our answer can only have 2 sig figs. So the only one here that has 2 sig figs is 3.7 times 10 to the minus 7th. The student measures the mass of a precipitate for 6 trials using the balance shown below and calculates the average of 3.43867 grams and the sample standard deviation of 0.04, 0.00439682 grams. How should the report the result? Rule 1, report the error with one significant figure unless it begins with a 1 or 2. Report the answer with the same precision as your error. That 6 will have the 8 round to a 9. And then are we doing better than the instrument? The instrument is 0.01. Yes, we're doing better than the instrument, so we can't use this. We have to go 3.44. We can't do any better than this. Excellent. You measure the mass of 3 aliquots of DI water using a balance that has 4 decimal places and get the following masses. You calculate the number of moles of each aliquot using a calculator. The calculator for the first sample and calculator output are are as follows. The average number of moles and sample standard deviation for all 3 outputs show up on your calculator as 0.316645 plus or minus 0.120. How should we report this result? Rule number 1. Report the error with 1 sig fig unless it begins with a 1 or 2. Does it begin with a 1 or 2? Yes. Plus or minus 0.0012. Rule 2. Your answer must match that number, 0.1366. Rule 3, are we doing better than the instrument? So what is the instrument in this? Well, here we have 5 sig figs. Here we have 1, 2, 3, 4, 5, 6 sig figs, which means the answer, our error, instrument error, will be 5 sig figs, right? So we have 1, 2, 3, 4, 5 sig figs. So it's in the 5th decimal place. That's our instrument response in moles, because it's the 5 sig figs in grams from this, 6 sig figs in grams from the conversion. So we're in our 5th decimal place. So 1, 2, 3, 4, 5. So what's bigger, right? The 0.0012 is definitely bigger, and so that will be our answer. You measure the mass of 3 aliquots of DI water using the balance that is 4 decimal places, and you get the following way to calculate the number of moles. For your first sample, your output is this. The average number of moles and sample standard deviation 3 aliquots show up as these numbers. How should report be reported? Rule 1. Report your error with 1 significant figure unless it begins with a 1 or 2. This begins with a 9. The 4 does not have a round. You must match your answer, right? That 7 causes the 8 to round, to the error. Then you must compare it. Number 3, are you doing better than the instrument? Here we have 1, 2, 3, 4, 6 sig figs and 3 sig figs, which means our answer, multiplication, can only have 3. 1, 2, 3. Our error in moles is in the 3rd decimal place. So what is bigger? 0.001 or 0.009? Well, 001, so we can't use that, so the answer is going to be 0.555. That is no good, right? And our answer is the one at the bottom. Excellent. A student measures the mass of precipitate using 3 different balances that show 5, 4, and 3 decimal places and records the following rules, values, and there they are. The average is calculated, and the result from the calculator is given. Report the average with the correct number of sig figs. Well, let's do the math. 128.43178. 130.626. And 120. Oh, look at that. There's an error. This should have another 0 there. I'm going to have to go back and double check, make sure I accept 2 answers on this. Poop. 6.720, because it should have 3, 4, and 5. We should be limited to 3 decimal places, so the correct answer should be this. But because I gave this, I'm going to have to go back and double check and take E as well. I just discovered that. Always good redoing these. Yeah. So if you see this and your thing has not been corrected yet, don't worry, give me a day, it'll get done. Okay, moving on. You measure the temperature of your solution 4 times and calculate the average and standard deviation is 32.8 plus or minus 0.13. You later find out your thermometer is not calibrated, is reading too low by 6 degrees Celsius. How does this new information affect the average and standard deviation? Select one. Well, let's talk about it. We have 32.8 plus or minus 1.3. Excellent. But we are reading too low, right? In reality, the temperature should be 38.8, right? But what's our error in that? How is that affecting our standard deviation? Well, there's a few ways you can test this. Here's a real easy way. Let's do the math. Let's figure out what the 3 numbers are that gives you the standard deviation. Well, that's easy. 32.8. We'll add 1.3 to it. So 3 to this will be 1. And then 2 says 34. Is that right? Yep. And then we'll minus 1.3. So that's a 5. And then a 1. Okay. So the average of these 3 points here is going to be 32.8. What's the standard deviation? Okay. Well, let's do a calculation on it, right? Remember, our standard deviation is simply the sum of the value minus the average squared. It looks like cubed. Squared divided by n minus 1 square rooted. This number does not change. It's still 3 measurements or whatever it's going to be. What we're really interested in is how does this affect x minus x bar, right? If this value changes, then the standard deviation changes. Okay, let's actually make this a little easier. Let's say our average number was really 30. We had, let's do even easier. Let's say our average temp was 10, 9, and 11 were our 3. So we get an average of 10. And it's off by, 10, right? It really should be 19, 20, and 21. Okay, so let's do the math. If this is the average of 10, right? If the average is 10, 10 minus 9 here is, is minus 1. This is 0. This is plus 1. So this whole term is this squared added together. Well, let's see if we do a shift, what happens here, right? This is 0. This is minus 1. This is plus 1. So anytime you do a shift, your standard deviation, your error, does not change, right? This should be hopefully pretty obvious mathematically. This is why we do this together in class, why we actually do this calculation together. So we have a shift in temperature because we know a calibration is off. This is a systematic error. It does not affect the random error, right? It's a systematic error. This is a random error. It does not affect it, okay? So how does this new information affect your standard deviation? The average is actually 26.8, but the standard deviation is unaffected. Incorrect, going the wrong way. The standard deviation is actually 6.06 degrees C, but the average is unaffected. That does not make sense. The standard deviation is actually 7.3, but the average is unaffected. No idea where that came from. The average is actually 38.8, and the standard deviation is unaffected. Yes, that is true. And the average and standard deviation are both affected and should be recalculated with the correct values of temperature. Nope, no need, right? If you were on a scale and it's off by 10 pounds, you just add or minus the 10 pounds, right? The error for that is still the same. 18. Okay, select all statements that are false, okay? And you can select 1 to 5 answers. Random error shift results in both directions. That is true, right? Systematic errors, in theory, can be identified. Yes, we can use a standard to find them, right? Or just like in experiment 4 in the lecture, we talked about, hey, you don't want to get this too hot, otherwise, it'll destroy the peroxide. That's an understanding we've identified a systematic error. Random errors always have a Gaussian distribution. Yes, they always do. Repetition of measurements will not reveal systematic error. This is true. If you have a short ruler right? And you continually measuring someone, they'll still be 9 foot tall every time you measure them. So it will not reveal that systematic error. Random errors can be made smaller by increasing the number of trials. No, you just know the error more. You know the error better. You can never remove the error by doing more and more measurements. That error is a function of the experiment and the experimentalist. So the answer is E. After 49 trials, the average mass delivered from the pipette is 24.0 grams with a standard deviation of 4.5 grams. If you perform a 50th trial, what is the probability the mass will be lower than 24.0 grams or greater than 33 grams? Select one. Okay, there are two ways to solve this. I'm going to show you the mathematical way first, and then I'm going to show you how to cheat do it. So here's our curve. Here's our average, which is 24.0, right? And we're interested in some standard deviations away from it. So let's do 4.5 standard deviations up, right? So this would be plus 1 sigma, right? And that puts us at, let's see, 28.5, right? And then at 2 sigma, right, we'll be at 33.0 grams, right? So, or we want greater than this. So we want all the area under the curve to the north of this. And they want everything lower than 24. Okay, so let's do this first. 2 standard deviations. 1 standard deviation is 68. 2 standard deviations, everything in between here is 95%, which means outside combined total is 5%. So you have 2.5 on either side. So over here, everything past the second standard deviation up, 33 up, is 2.5%. Now, I'm asking you for everything below 24, right? Everything under the curve is 100%. Everything to the left of this would be half the curve, or 50%. Right? So our answer is 52.5%. 52.5%. Here's the way to cheat. If I know I need everything to the left of 24 and then a little bit extra, it has to be bigger than 50%. It's the only one greater than 50%. So that's the short way to solve the problem. Select a true statement about RSD. Select one. More than one of the statements is true. Okay, well, let's come back to that one. The sample RSD equals the population RSD when the sample average equals the population average. Wow, that sounds good. Now remember what we learned in class. As small n approaches the population n, we learned two things are true. The standard deviation approaches sigma, right? The sample standard deviation approaches the population standard deviation, and the sample average approaches the population average. We know nothing. Only when n approaches big N. Not when average approaches average. Because remember, I actually have an example where we have a sample where the average actually approaches the average when we do the sample of jockeys and NBA players, but the standard deviation is way out of whack, right? So we actually did an example of that showing that even though you do have the same average, right, that's not the case. In fact, the average can go back and forth across there as it settles to the actual amount as small n approaches big N, right? You don't know what it does before this, okay? Because there are several times when the sample average will be equal to the population average. But that doesn't mean that the standard deviation will be equal, which means your RSD will not be equal. Okay, none of these statements for this, so this is false. None of the sample statements for this question are correct. We'll come back to this. D, the sample RSD approaches the population RSD when the sample size approaches the population size. Okay, this is what we've denoted here, right? This is the big qualifier, when the sample size approaches the population size. However, look, we don't talk about RSD here. We don't talk about it at all. So what do you need to think about? Well, what is RSD, right? RSD is simply standard deviation divided by the average. And both of those approach the population values as n approaches big N. So this is absolutely true. I'm just combining these into one term, which is RSD. Okay, let's look at E. The sample RSD provides information about the accuracy of measurements. No, it provides precision, so this is false. So none of the statements for this question are correct. That's false. And more than one statement is true. That's false. There's only one correct answer, and that is D. This is a challenging question. It's designed to be. Okay, how do you report an average and its corresponding standard deviation? Select one. The average and the standard deviation should have the same number of significant figures and the same number of decimal places. Oh my gosh, that's awful. That's absolutely false. The average should be reported with one significant figure. Unless it begins with a 1 or 2, then it reported with 2. That sounds great, but it's not the average that should be reported that way. It's the error, so that's false. The average should be reported to the same decimal place precision as the standard deviation. Yes, if your standard deviation is this, then your average should be reported as that. True. This is directly from the rules. Copy paste. The average and standard deviation should have the same number of significant figures. That's just awful. And none of the above. Nope, we do have one. That is true. So 21 is C. Select all statements that are true. The percent error provides information on the relative accuracy of one measurement to another. Absolutely true. Percent error is what allowed us to compare the volumetric pipette to the grad cylinder to the beaker in experiment 1. Systematic errors contribute to the percent error. Yes, systematic errors, percent error reports on the systematic error, right? Random errors do not increase or change percent error at all. Absolutely true. Random errors revealed with repetition of measurements. Absolutely. The more you measure it, the better you know what that error is, right? That's why n equals 10 is better than n equals 3. It doesn't get rid of it, but you know it. You reveal it. You figure it out. True. Systematic error can sometimes be revealed by using a standard. Absolutely. If you have, like our example we keep using in class, that that measuring tape that has been shrunk, if you compared that to a NIST standard ruler, you'd see it's shorter and would reveal your systematic error. Random errors reflect statistical fluctuations associated with a measurement. Absolutely, right? And they represent that with a Gaussian. So in this one, the correct answer was all of them. 23. You are performing the standardization and titration to determine the molecular weight of an unknown acid. Wow, this looks very familiar. The calculation for a representative trial is shown below. When applying the third rule of reporting errors, what should we consider to be the instrument error? Select one. Okay, well, let's figure out the instrument error in grams per mole using all the inputs. Okay, here we have 1, 2, 3, 4, 5, 6 sig figs. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We have 5 sig figs, 5 sig figs, 5 sig figs. So here we have 1, 2, 3, 4. It's on the 0 here, okay? And that goes down here. So we have 5 sig figs for this as well, okay? Here we have 5 sig figs, and here we have 1, 2, 3, 4, 5 sig figs. So our answer should have 5 sig figs. 1, 2, 3, 4, 5. Which means that's our wiggle spot, right? And that is going to be the error for our calculation. What is the correct reading for the burette on the right? Okay, well, let's see. Is it larger than 6.3? Yes. Is it smaller than 6.4? Yes. So we are at 6.3. Okay. So 6.3, this is 0.05, 0.06. It's around 0.07, so 7. And then, I don't know, I'll give it a 1. Okay, so there we go. And now you could have said 2, and then this would have... The key here is how many decimal places is it, right? So this has too many decimal places, cannot be the right answer. Not enough decimal places, not the right answer. Once again, 6.4 is too big. So this is the only possible answer for this question with the right sig figs. You get a new job in a deli weighing cold cuts, potato salad, and other food for customers. Delicious job. Last Thursday, you place a container of pickled green beans on the scale balance, right? You take the container off the scale before you print the price sticker for the customer. So you have to place it back on the scale so you can print the price sticker. You notice the price on the computer now is less than it was the first time you weighed it. You lift the container on and off the scale and see the price goes up, and sometimes when you put it back on the scale, and other times the price goes down. You hand the delicious green beans to a confused customer and think about what you observed. Select 1. The balance scale has low accuracy. Accuracy is how close are you to the real mass? We know nothing about that. So we can't draw this conclusion at all. The scale/balance is not properly calibrated. Once again, this is the same question as this. It's talking about accuracy. Are you weighing the right amount? We don't care if we're weighing the right amount. We're just seeing that the scale is going up and down every time we put it on the scale. You observe fluctuations that arise from systematic error. Yes, we're observing fluctuations, but fluctuations don't arise from systematic error. You observe fluctuations that arise from random error. Absolutely. This is exactly the definition of random error. Every time you repeat a measurement, it's a little high or it's a little low, and there's statistics behind it. So this is true. The scale is accurate and has high precision. Once again, we can't talk about precision. This falls right with these first two. So the last answer is D.